Okay, so welcome everyone. It's my pleasure to introduce our final spotlight speaker for today. Robert Krauthgamer is a professor and department head at the Weizmann Institute. He's broadly interested in analysis of algorithms, including approximation algorithms, graph algorithms, metric embedding, high-dimensional geometry, and in particular, he has a great collection of works on algorithms for massive data. And today he will tell us about courses for clustering in graphs and beyond.
Thank you very much, Peter, and thank you all for organizing this workshop. It's a lovely program, very interesting. So I'll tell you about coresets for clustering, and then the twist here is clustering in graphs. And this is joint work, and I'll explain, of course, the term coresets. And this is joint work from two papers. So overall with Vova Braverman, Lingshao Huang, Xiaofeng Jian, and Xuan Fu. All right, so let's see if I can move this. Okay, good. So clustering is, of course, a very basic task in analysis. So generally, you have a lot of points, and you want to cluster them. There are different ways to measure this thing. It has a lot of applications. Essential tool. So you show here a few examples. I'm going to focus here on distances in graphs, even though usually it's or one of the well-known contexts is clustering of Euclidean points. I want to focus on graphs. So let's see what I'm doing. How do I move this from? Sorry, just a second, because it obstructs my screen. Okay, good. Okay, so the typical setting is Euclidean. Let me start with a typical setting, this Euclidean setting. So you have maybe n points in Euclidean space, let's say of dimension d, and you want to partition them into k groups. So it's sort of like we know that the number of clusters is k. And often it is framed as an optimization problem, which is the one called k-median. So the goal is to choose k center points in this d-dimensional space. So I'm going to denote them by c, c1 up to ck, or the set c. And you want to map basically every point xi to its closest center among the k centers. And you want to minimize the objective, which is the sum of distances to the centers. Okay, this is like going to be, this is called k-median. We're going to focus on this. Of course, there are other versions where you take sum of squares, etc. So the clusters usually would look something like in the example here on the right, as opposed to like other examples on the bottom, which doesn't fit this, but there are ways to deal with it. So this is a very classical setting. And what really fascinates me here about this problem is that it's possible to do this data reduction. So this is a concept that was suggested by an earlier paper, but I'm going to use the notion from Harpeled and Mazumdar called Strong corset. So in this strong concept, you basically reduce the data. So you want to place it from a huge, potentially huge data set X with a small, hopefully, set S, such that if you try to optimize or evaluate, sorry, the function f on your data, on the small data set S, it's up to 1 plus minus epsilon, the same as as evaluating on the big data X. Now, the crucial thing here is that this should hold for any possible set of centers, of k centers. So it's a very strong requirement. It's not only that the optimal clustering agrees between X and the reduced S, but actually any possible clustering agrees. So any possible means every choice of k centers. Now, the way to do it is usually to take S to be a multiset. So it's like a set of points, usually a subset from X, but give these points high multiplicity. So if you want to represent them, or what we call the size of the set is really the number of distinct points. But because they have multiplicity, they have the same performance, because this f is really summing over n points. So in a sense, you're still summing over n points. It's just that you're summing over few points with high multiplicity. So each point contributes a lot. So here is like a simple illustration. Suppose you have original data set X. We have n minus 1 points clustered and 1 point far away. Then intuitively, it makes sense to replace that cluster with 1 point of weight or multiplicity n minus 1. And that point that is far away, there is not much you can do. And you can prove where does this work well. Now, if you want to have something like epsilon error or something, maybe instead of clustering all these n minus 1 points into a single point, you take bunches of something like epsilon n points, then you come up with a representative for them. You give that representative point weight epsilon n, and then you have 1 over epsilon. such points. So that is usually where this epsilon comes into play for this epsilon error. So this is a very powerful technique. This is like a mental picture. This is not how the algorithm works directly, because we have to, of course, do something more general. So this is a very powerful technique because it can compress the data, and often the way it is done is actually without clustering the data, like finding the optimal solution. So you can do it as a pre-processing to the actual clustering step. So it's very, very powerful because you can do this, and then you can apply the optimization that you want, say an approximation algorithm or p-TAS or something else on the small data set. And if it's very indeed small, then of course now a relatively slow algorithm on the small data set is not so bad. So the question is how much time it takes to compute this Coreset. However, I'm not going to focus on that. This is usually comes sort of like for free or straightforward from the implementation. We're going to focus on the size, on how much can you reduce the size in principle, like does it exist at all? And then there's an issue of how to implement it fast. Okay, so this is widely applicable. There are also applications for this concept in distributed settings, in data streams, because, for example, distributed, instead of sending big data set, you send a small data set, and so on. And this area is, this problem or setup has attracted a lot of work, and there has been a rapid development, a lot of results. So here I'm focusing, remember, on Euclidean case. I would say, roughly speaking, there are like 3 waves. I'm not sure if it's allowed to say these words these days. There's a lot of connotations, but 3 waves of results. So the first wave of what I call here first generation, the bounds on the size of the Coreset, the number of distinct points that you have, was exponential in D. Remember, D was the Euclidean dimension. So this was exponential in D. Actually, the first bound, like 0th generation, also had something like log n. So it depends on the size of the input. Now, this first generation does not depend on the size of the input, so it goes down to a relatively small size, independent of how many points you started with. So the second generation sort of like removed the exponential or improved the exponential dependence into polynomial dependence on D. And then sort of like the third generation, which is like in the last couple of years, we get dimension free, independent of dimension. So basically, there's no need for dependence on this, which of course fits very high dimensional scenarios, because you don't want to depend on the dimension D. Intuitively, what happens here is that basically you replace D with K. Intuitively, what happens is I never need dimension bigger than K. If I only have K clusters, in effect, my dimension is K. Okay, that's the intuition, but of course to implement it is more difficult. Now, if we want to talk about techniques, then I'd say it's something like this. The first generation used to discretize all directions. So you have in D dimensions, you have something like 1/epsilon to the D, many directions in space. The second generation used sampling, actually important sampling. I'm going to talk about it a bit more. So you sample independently, and then it naturally gives you dependence on the dimension. And the third generation is sort of like get around this dependence on dimension by using dimension reduction. So for example, what I said before, if you have high dimension, if you're in a very high dimensional D, then maybe you can say somehow, in effect, I only care about a K-dimensional subspace, maybe like the subspace that goes through the centers. And somehow I can replace that D with K, somehow reduce this, the problem into RD in a sense. Okay, so this is the Euclidean setting, which has been a lot of work, attracted a lot of work. But I want to talk today about graph metrics. So in graph metrics, this is a new setup that we came up with, basically, I mean, for Coresets, but it was studied in the K-median context for a lot of time. So you suppose you are given a graph, and then the graph has, the edges have lengths, and you can compute shortest path metric in the graph. So now here in the graph G that we have, both the data X, these are the points that we want to cluster, and C, the potential centers, they have to come from this graph. So if you talk about general graphs, then basically it's a general metric space. Yeah, we still have the same K-median objective, but the motivation for this could come from different types of graphs. So some graphs could be, say, like if you take even a binary tree, infinite binary tree, and that's one fixed graph where the names of every vertex represents, you have the names of 2 vertices, you can evaluate the distance between them. Or some graphs that you sort of like build from data, like a social network or road network, And these may have some extra features that are typical to, say, road networks. And you might want to use these features to say that it is not a worst case or general graph. Okay, so what is known about K-median in graph metrics? I don't want to go into this too much, but there has been a lot of work. This is not the course, it's just like optimization problem. So for example, you can see here that we assume K is part of the input, so it's not a fixed K. And then the problem is NP hard, and there's some approximation. The factor that is still hard, there's some approximation algorithms known. What happens if it's a planar graph? What happens if it's a bounded tree-width graph, and so on? Certain restrictions. So people have worked on this in different settings and spent a lot of effort on approximation in graph setting. Sorry, on approximating K-median in graph setting. And what we want to study in this work is corsets for this problem. So somehow say, without solving the problem, I want to reduce the size of my data. And then hopefully you can implement all the algorithms in previous slide much faster, for example. Okay, so one of the main results is this theorem of Feldman and Langberg, because it introduced a very powerful technique based on sampling. So this says that in every endpoint metric space, they actually look at Euclidean setting, but one of the results applies in arbitrary metric space. So in arbitrary metric space, you can, there always exists a corset of size. So there's O tilde, I'm just going to call it O throughout. So it omits polylogarithmic terms. So the corset size is something like epsilon to minus 2 times k cubed times log n. So remember, log n is really depends on like the input metric space. So if the metric space is really large, sort of like it comes into the size of the corset here. So this is an interesting aspect. You really need this dependence on n. Now I should mention that I've listed here k cubed in some later work, in particular their own work, like they posted later improvements on the archive of like a full version of the paper, improves this to, instead of k cubed, to linear in k. But I kept this for the timeline aspect. Okay, so what about this dependence on n? Can you get rid of it? So one reasonable conjecture is to say that if you have a graph, a special graph family, something like Euclidean, like Euclidean space, you don't need this log n. You need a dimension d, or even you can get rid of that, we said. What happens if it's a special graph family? Maybe it's a tree or planar graph. Can you then get rid of log n? And we actually conjecture that it's impossible to do for general graphs to get rid of the log n. Like for general graphs, there has to be dependence on n. So in the first of the two papers, we actually focused on bounded tree-width graphs. And we showed the following theorem, that every graph of tree-width t, or some, admits a corset of size epsilon to minus 2, k cubed, but now the tree-width of the graph. So the tree-width is some sort of like way to bound the generality of the graph. I'm going to talk about it in the next slide. If you're not sure what it is, think of a tree for now. So a tree has tree-width 1. So moreover, you can construct it quickly, something like almost O of nk times, so number of points times k. It's close to linear. It extends to like more sophisticated versions of the problem, extensions of the problem. And we also show another theorem, which is actually a lower bound. So if you're given parameters epsilon and k and t stands for the tree width, then actually there is a graph with tree width t, for which every corset will have to have large size. How large? So what the bound that we prove is epsilon to minus 1 times k times the tree width. So it has to have linear dependence on the tree width. Okay, so if you compare to the upper bound has linear dependence on tree width. The lower bound has linear dependence on tree width. So at least in that parameter, we are tight. In the other parameters, you can see we're not tight. So one reason it's interesting is that it shows that you cannot get completely independent of the graph, right? Because this tree width parameter can be larger and larger. And indeed, if you look at our proof, the size of our graph is actually 2 to the tree width. So if the size n is like 2 to the tree width, so you could translate the parameters, it really shows that for graphs of size n, there is a lower bound of omega log n. Right? So there's a lower bound that the corset size must be omega log n. Okay, just because the way we construct it, the tree width is, the size of the graph is only 2 to the tree width. Okay, So just a word about tree width, because I mentioned it and I didn't define it. So it basically measures how the graph resembles, how close it is to a tree. If it's a tree, it's, that this parameter is 1. In worst case, it could be n-1, for example, for a click. And the way I like to think about it is, which is equivalent up to constant factors, this is the smallest parameter t, such that you can always find a vertex separator of size t. Always means in every subgraph of G, not only in G itself, but also in every subgraph. So for example, in this two-dimensional grid that I show you here, you can find a separator, like balance separator of size t. And this is also true for every subgraph of this graph. So it's sort of like a canonical example for tree width t. But remember, we also have edge weights, which may distort distances quite significantly. Okay, so this is about tree width. So this was the progress we wanted. But another question we had in mind was planar graphs. Right? So planar graphs, it's known that they are not necessarily, do not have bounded tree width. The tree width could be square root n. So these results that I just showed you in the previous slide do not apply to planar graphs. And this was actually a problem that we were really, let's say, bothered with and we really wanted to solve. And then in the second paper with Braverman, Jiang, and Wu, we managed to prove it. So this is a new paper. And we managed to find, like, show that every, graph that is, say, planar or even excludes a KR minor, so that's a generalization of planar graphs with parameter R, admits a coset of size about O of epsilon to -4 times k squared. So there is some dependence on R, which is the size of the minor. So for planar graphs, this is basically the result. You can see here up to the O tilde. When, if you want dependence on R, then actually I must say that it's not so good. It's theoretically satisfying, but practically it's probably not very good. Because it depends on some theorem in which the dependence on the excluded minor is not very explicit, so I don't even know to tell you what it is. But for planar graphs, actually we have the simple version of this theorem, like then we extended it. So there are no huge constants here for planar graphs. And moreover, this can be constructed in linear time, so almost linear time, so it's very effective in this sense. So once we solved planar graphs, let's say, we actually looked at the framework, which I'll tell you in a minute, what is that, the framework to build this. And we realized that the same framework or similar framework actually can give us more results. So the theorem 4 here actually gives a bound for graphs of bounded highway dimension. So this is going to be too much of a digression to explain what is the definition, but this is some parameter of graphs that was used in connection with road networks to say that if you want to go between two cities, sort of like you have to go through major junctions or major interchanges. And this is the characterization, mathematical characterization that reflects this. So if this highway dimension is bounded, which is supposed to hold for road networks, then we can find coset with some bounded size. So the bound here is maybe not that great, but it's independent of n. So we have some finite bound here. And the fifth theorem, which is perhaps the most surprising, goes back to the Euclidean case. So we designed this framework to solve planar graphs. But then somehow we realized that it actually works also for the Euclidean case, which is what I started with, which was studied a lot, for which there are like very, very good results mentioned here by Huang and Vishnoi, like from very recently, from Stock 2020. And what we can do using our framework is basically obtain a coset whose size is again O tilde of epsilon to -4 times k. It's very close to what you have in the theorem in the top, actually slightly better. And this matches the result from Stock 2020. It's independent of the dimension, so it's dimension free. I think it's a little bit, it's simpler. Our proof is simpler than theirs, and I'll tell you about this. And it's really satisfying that by looking at a different model of graph metrics, we came up with a framework that is like very nice, very efficient, very useful. And somehow we got almost for free an optimal, for now, optimal solution for Euclidean metrics. So it's not known to be, it's the best currently known, but it's not known to be optimal because of this epsilon to -4. We don't know whether it's optimal, and presumably it's not optimal, but this matches the best result known with very little effort. Okay, so I want to tell you about the techniques a little bit of these all these results. So basically, let me use one slide to describe this Feldman-Langberg framework, which is based on importance sampling. So suppose we fix a metric space M, maybe it's a graph, Euclidean, whatever. Now, the idea is to compute for every point some importance, some score. I'm going to call it importance P sub x. And then we're going to normalize it to 1, so it looks like a probability distribution over the points. And then the second step, you just write the correct number n of samples from x. Each one, you just use this px, this probability that you computed, because they sum up to 1. So you repeat this sampling n times, you get n points. Okay, so this guarantees that what you obtain is a set. It's going to be a coset of size n, and you give each point that you sample the weight, which is 1 over px. So it's easy to see that this 1 over px gives it exactly sort of like this unbiased sampling properties. That's very reasonable or expected, why you give this high weight, 1 over px. And then the big question is how to set n. So the intuition, because I'm not going to go over the entire argument, which is not so short, is how to set n. Well, basically, suppose you had only one center set C that we cared about. Really, C could be, say, any choice of k centers. But suppose we only had one choice of interest for us, maybe the optimal choice. Then, because you're doing sampling and it's unbiased, it's easy to see that the objective is concentrated. You use something like Hofding bound. You see that up to 1 plus epsilon, with the right parameter of n, you get that the objective with respect to the sample, if like compared to objective with respect to the original data x, right? So the algorithm on top, I didn't write it here, this generates the set S, our coset S. And you want to compare the objective on S versus the objective on the input X. And they're very close, there's standard concentration. But what happens when you want to deal with all possible center sets? So now you need to do like a union bound over, like in Euclidean case, Euclidean setting, the number of choices for the centers is infinite. You're not going to do a union bound over infinitely many choices. So you want to do a more clever union bound. The way to do it is to, like if it's a graph, you want to have n choose k center sets. This is all, again, too much. So instead, you're doing something clever by using something similar to this Sauer-Schellach lemma from pack learning, which is based on VC dimension. So it sort of like reduces the number of bad events, the size of the union bound. And therefore, you can use the same concentration, but with better parameters. Okay, and overall, what you get from this, and this is from the FL11 paper, if both data sets, the data set X and the center C, they come from this metric space N, and it has this what's called weighted shattering dimension, some bound on the weighted shattering dimension, which I'm going to call here S dim, that depends on the metric space. So then the number of samples that you need, this n that suffices, is epsilon to minus 2 k cubed times this shattering dimension. So this shattering dimension depends on the space, and then you can prove, for example, that in Euclidean space of dimension d, this is no more than d. Right? This is one thing you need to prove, like to bound this shattering dimension. And the shattering dimension is sort of like, you can think of it as like the cousin of VC dimension. It's really close to VC dimension. You can, up to logarithmic terms, they're the same. Now, as I said, this k cubed was proved initially, then it was improved to k squared in its generality. For this generality, not for Euclidean case, you can improve to k squared, not to k. Using, this was done by Braverman, Feldman, Lang, and then by Feldman, Zoller, Schmidt. There are some refinements of this argument analysis. Okay, so we want to use this theorem. I want to use this bound. So I can get this bound with epsilon to minus 2 times k squared, but I need a good bounded shattering dimension. So the natural thing is to take this graph, say, of bounded tree width and prove that their shattering dimension is small. And indeed, we can show that for every graph, G, the shattering dimension is at most order of the tree width. Once you prove this lemma, you go back to the previous slide, you plug it in, we get the result that I stated before. Okay? For bounded tree width. You just need this lemma, which bounds the tree width. And I'll tell you a little bit how you prove this in a minute. Now, what happens for planar and excluded minor graphs? So basically, this is open. So we wanted to prove this. We don't know how to prove this. So we had to go around this barrier. Now, I should mention that something close to it is known, but it's a bit too weak. This is sort of like a uniform version of this shattering dimension. So then it's bounded, but it's not enough for our purposes. That's why I mentioned before the weighted shattering dimension. There are two notions, sometimes using the same name, but they're not the same. So basically, to get the planar result, our approach is to bypass this barrier because we don't know how to solve this open problem. And we have two ideas that we use to bypass this barrier. So the first idea to bypass the barrier is to reduce the data set. This is like a very naive idea. You say, I have endpoints. I know how to reduce them to log n. We saw that I discussed it in one of the earlier slides. You can go from n to log n. Then why not do it again? You go to log n, then again and again, then you get to order 1. So of course, I omitted here the parameter k. You're actually going to k log n, then to k log of, etc. So, but eventually you're supposed to get to order k, not order 1, but or something similar. So why does it not work? Because that sounds very powerful. Well, the problem is that the obstacle is that n is actually the total weight of the points. So when you go from n points to log n points, as I suggested, you're going to get log n distinct points, but their total weight is still n because you're doing this sampling, and if you sample a point, you give it a high weight, inversely proportional weight. So the total weight remains n, which means now you cannot go from log n to log n. You're not really in the situation of going from being at log n. The total weight is still n, so you cannot apply it the second time. Okay, so this naive approach fails. However, we can still save something and apply this approach by introducing something which is data dependent. It's a version that is data dependent. So our analysis of the shattering dimension depends not only on the metric space, but say it's a Euclidean dimension, Euclidean space of dimension d, then you say, well, the shattering dimension is d. So no, it depends also on the data. So if I get smaller and smaller data, this what I call here the L0 norm of x, because I think of x as a set with weights, set of points with weights. Maybe in the beginning, the set of points with each one has unit weight. Then when I go to a coreset, I have fewer points, but with high weights. So I use this zero norm notation to count the number of distinct points. So I want the shattering dimension to depend on, I allow it to depend on this zero norm of x. So now instead of going from n to log n, this is really measuring the number of distinct points. So now the number of distinct points can go from n to log n to log n, and so on. Okay, that's the approach. The total weight will stay n throughout, but the number of distinct points will satisfy this sort of like iterative reduction. Now, another way you can think of this shattering data-dependent invariant is if I'm in a really, really high dimensional space, but all my data lies in a low dimensional space, then maybe I don't care about the fact that M, the metric space, is high dimensional. I only care about X, my data. Okay, so somehow this shattering dimension should depend on M and X like together. And somehow if X is small or good in some sense, this will be a small number. So that's the first idea. And then to implement it, really we run into problems. So we need another idea. It's like this number 2. This is what I call it here. It's not the way it's written in the paper, but I call it here shattering dimension of M and X epsilon. So what is this X epsilon? This is something which is similar to X or similar to the metric, but distorts distances up to factor 1 plus epsilon. Since we don't care about distortion, if we distort every distance by 1 plus epsilon, the cost of any clustering into any K centers will not change by more than 1 plus epsilon, which is something that we allow anyway. Okay, so we're going to lose epsilon here and epsilon from the other lemma, so together it's like 2 epsilon over pi. So I call it here SDIM of M, comma X epsilon. This is not like in the paper, but this is the intuition, that is what the meaning, that it allows distortion. Now, why do you need to apply this distortion? The idea is that once you apply the distortion, the distances change so much or enough so that the shattering dimension, maybe it collapses to a very small number. So even though the original distances have sort of like large shattering dimension, or potentially, I don't know, because I don't know how to analyze them, I apply some 1 plus epsilon distortion, and then I manage to get a low shattering dimension, and then it's very effective because I can apply the theorem that we've seen before by FL11, that you only pay proportional to this shattering dimension. Now, one important comment here is that this new metric up to distortion doesn't have to be really a metric. It doesn't have to satisfy, say, triangle inequality. And moreover, and that's very useful, it doesn't describe really all the distances in the metric. You only need to sort of like apply it or calculate it on the distances from your data points, x, to the rest of V. So for example, in Euclidean setting, if you have like n points, I only care about the distance between my endpoints and the rest of the space. I only need to reduce the distance between them. And if I then change from n to log n points, I only need to worry about log n points to the rest of the space. So I have this advantage. And this is sometimes called in that literature terminal embedding. There are a few points of importance called terminals, and you care about distortion of distance between them, the terminals, and the rest of the points. So going back to excluded minor graphs, what we are able to prove in this setting is that the shattering dimension, okay, so what you see here is shattering dimension of the metric coming from, say, planar graphs, after distorting the distances by a little bit, by 1 plus epsilon, this can be bounded by epsilon to -2 times log the number of distinct points. And this suffices to prove the main theorem. Why? Because if I go back, right, so now the shattering dimension depends on epsilon, etc., but depends on is like log the number of distinct points. If I go back, let me go back to the previous slide, this FL11. Here at the bottom, you see that the size of the course is going to be epsilon -2 times k cubed times the shattering dimension. If I apply this modification of this theorem, now I actually manage to reduce the number of points to log the number of log n. But now the next time I have log n distinct points, I can apply it again and get to log n distinct points. Okay, so the fact that everything depends on the number of distinct points is very powerful here, because now I can apply this idea one of like going from n to log n to log n and so iterate this way. Now the idea to get this is really to bound this shattering dimension is to get this terminal embedding, this like from the top bullet. I have to somehow change the distances and only the distance from the terminals, from the points that I care about to the rest. So that by distorted by 1 plus epsilon, so that now the shattering dimension can be bounded. But I don't require an order 1 bound. I can do something that depends on the data. This log the number of distinct points in X is very powerful because it sort of like adds more room. Usually what we try to prove is like a constant bound, epsilon to -2 or something like this. Here I have this extra log factor that helps me design such an algorithm. Okay, and basically if you wonder how do you get these things, there are references here by Eisenstadt, Klein, Matthew. They use sort of like a decomposition of the planar graph in a certain way, and which in turn builds on what's called shortest path separators that go back to Thorup. And to extend it to exclude minor graphs, we use a generalization by Abraham and Gavois. So these are like part of the technical details, but this is the way we actually use the excluded minor information. Now for bounded highway dimension, we also bound the shattering dimension. Here there's no dependence on this 0 norm of X. So this you don't need to iterate like go from n to log n, etc. Because this is in one step direct. But here we use a different terminal embedding. So unlike what in the top it says factor 1 plus epsilon distortion, here we use something very different, which is an additive distortion. So it's some terminal embedding, but allows some additive distortion in a controlled manner. And somehow we get this, after this distortion, we get a low shattering dimension. Okay, and finally, and this was what I said is a very surprising but satisfying point, is that for Euclidean metrics, actually you can get very, very easily a bound that says that the shattering dimension, so it's very easily given known work. You get the shattering dimension is at most epsilon to -2 times log the L0 norm of X. Okay, so once you have this, it means that you can go from n points to log n distinct points by one application of FL11. Then you apply it again. Oh, it's a modification of FL11 with this SD bound here, right? Every time you change, you distort things by 1 plus epsilon, but it's not the same epsilon. It's like decreasing geometrically, etc. So eventually you get to constant size. So this is a very easy way to get the best result for Euclidean metrics. And the thing here, the thing here is that the bound that we get on the shattering dimension has dependence on the input. This log, but instead of log n, it has log the L0 norm of x. This small change makes a huge difference. Because once this is relatively easy to get, and once you get that, and the rest of the framework, you get everything immediately. Now, to get this, why it's so easy, it's basically because it's sort of like a version of JL. It's not clear from this description, but basically there is a version of JL. It's called terminal JL, exactly for this name, because where you care about the distance between a few points and the rest, all the points in the space. And you can reduce the dimension by this terminal JL theorem of Narayanan and Nelson. Once you reduce the dimension, you're in a Euclidean space of small dimension. And in Euclidean space, we know how to bound the VC dimension, sorry, the shattering dimension. It's just the Euclidean dimension is good enough. It's like the same bound. So you immediately get this, so you reduce to something like log k dimensions, and this k is really log the number of distinct points here, you plug it here, and you get the shattering dimension bound. So I don't want to focus on this. Sorry?
I wanted to mention that we have 5 minutes.
Okay. Yeah, so obviously I prepared too many technical details about this result. So if you want to talk about the shattering dimension, then basically, yeah, let me try to say something about this. So basically you look at the sort of like the VC dimension, but of balls, metric balls. So you take arbitrary metric ball in space. So this is denoted here on the top. And then the unweighted shattering dimension is basically you take a subset, an arbitrary set H, and you try to intersect it with all possible balls that you have. And you want to say the number of different ways you can get intersections with balls, the outcomes, they're only the cardinality of H to the T. If you have this bound, then the shattering dimension is only T. Okay, so if the shattering dimension is 2, it means that you only have H squared many such patterns. And this happens, for example, in one-dimensional line, because one-dimensional line, you intersect with a ball, you get like a sub-interval. So the sub-interval is characterized by 2 points. So it's basically the number of points in H, choose 2. That's the total number of patterns you can get by intersection with balls. This is the unweighted, the easy version of shattering dimension. What we need is actually the weighted version. In the weighted version, you have another factor, which is here, this V of Y. You have a weight for every point Y. This is not the center of the circle of the ball. It's actually the other points. And then you have to take these worst possible weights. And these weights completely ruin the geometry that you have in the one-dimensional case. Okay? So, for example, here you have this ball. If on point 8, Y8, I put a very, very small weight. Now you multiply by the weight, it seems like it falls inside the radius. So it changes completely the structure of the ball, because I can put, for any Y2, Y3, up to Y8, I can give different weights and decide which points are inside the ball and which are not. So, but somehow, the idea is that we can bound this. So, for example, for a tree, and then we can extend for bounded tree width, the shattering dimension is bounded by order 1. And this is because the weights are arbitrary, but they're fixed once and for all. So somehow you have to use this information. Okay, so I'm going to jump sort of like glance over the argument. Basically, the idea is to use portals. So if I look at the distance, say, between some point X and some point Y here in the tree, so I have this set Y, the Y's are this set H. Then I want to say that when you go from X to Y, you have to visit one of 2 portals, either this yellow point here I marked here by yellow, this P, or Y3. So somehow you have to go through these portals, and there are only 2 portals that are relevant in this case. I don't have time to go into the details. And basically say that distance between X and Y is the minimum between, sort of like using the triangle inequality, but going through the best portal. Right? And this is true. You want to go from X to any possible point Y that you might want to go outside. And this basically sort of like gives you classes of points X, because if I look at a different X prime, a different X double prime, they use the same set of portals. So I can write this description, and using the same set of portals, And that sort of like reduces the complexity of sort of like a VC dimension argument that I said before about union bound. Instead of bounding all possible X points, I have a few classes of them, and I bound each one separately. Okay, this is a very high level argument. Okay, so it's really important that you have few portals and you use these portals, and then there's some counting argument that you need to do there to bound the shattering dimension that I'm going to skip. At the end, it boils to an argument something like this. I'm going to skip here to the bottom. Suppose I have these linear functions, and I have only H linear functions, and I want to look at the ordering of these linear functions at any single point, like this vertical bar here. So how many different orderings do I get from these linear functions? So the thing is that if I move the vertical bar a little bit, the linear ordering doesn't change. They're sorted in the same order. If I move it a little bit, it doesn't change. But then at some point, two linear functions cross at these red points. Where is my pointer? Like at these red points. And then the linear ordering changes, right? So how many times can this happen? So if I had like cardinality of H linear or affine functions, the number of intersections that only pairs intersects, H squared intersections. So the ordering can only change H squared time. So if I look at all vertical bars going from left to right, the number of different orderings that I see is bounded. This is like a very, very simple lemma that we use in our argument somewhere. I didn't say exactly where, because we sort of like reduced to this case. And we reduce to something actually more complicated by using these distance via portals. Okay, so this is like the general argument, and it uses some known lemma from computational geometry about envelopes and these orderings. And now I want to say something about planar, and that's going to be like one last slightly technical slide. What happens in planar? Why is like we don't get the same result, or we don't know to get the same result? So we use a decomposition, what I call data-dependent decomposition, like we did in the tree, where you go through the portals. The thing is, so I don't have time to describe it, but we have to have something that depends on poly x, on the number of data points x. And then what it comes out to, when we do the counting, we have this poly x factor in this t, right? Remember, we have this h to the t. So that means the shattering dimension is log in that, because this t is in the when you do the counting, ends up being in the exponent, so it's log, something like this. So basically, we get in the dimension order log the L0 norm of x. Okay, so we get something that depends on this, which is not ideal. We hopefully can get rid of it, but we don't know how to do it. But this log of the number of distinct points comes from the decomposition that we apply in the first step. And then after we have the decomposition, and let me think of like using shortest path separator. So if you have points x and y on the left separated by shortest path, that means that you have to, when you go from y to x, at some point your shortest path hits that separator, then it goes along the separator, then goes to x. Now, the usual idea, very well-known idea, is to replace this path, which could be very, very long, with a few portals. These are the yellow points here. And then you say, okay, I'm going to approximate this going from y to x by going from y to the best portal, then going along the path, and then going from some portal to x. Okay? So this way, if I can manage to get few portals, then maybe it will work. Of course, I pay distortion 1 plus epsilon because I sort of like put epsilon space in between the portals or something, or powers of 1 plus epsilon, something like this. So this is where the distortion comes from. But the challenge is to represent this as sort of like linear functions. What you get here in this distance approximation of y to x is a summation of 3 terms going from y to the portal, then from one portal to the other portal, then from the second portal to x. Right? So summation with these 3 things. Somehow you want to, what I told you before, the lemma with the picture was about linear functions. This is like the sum of 3 approximately linear functions. So this is where you need to bound the number of the shattering dimension. And that's really where all the action happens, like the technical difficulty. Okay, so I'm going to stop here with this technical material. I just want to say that I think these corsets, we showed corsets, and it's still open whether you can get something like a good bound on shattering dimension for exclude minor graphs. I think one very interesting direction is that the dependence on epsilon seems to be have a gap. It's related to some very interesting questions about, say, sampling, like samplers or VC dimension, if you want. So there's a gap there between epsilon and epsilon squared. We have a lower bound, but it's for graphs of omega epsilon. So it's open both say for graphs and in Euclidean settings. And it seems to be like a relatively big gap here, and mathematically deep, potentially deep. And another direction is to use corsets for other objectives, and there have been a lot of papers on this in the past few years. So it has, because these corsets, have a lot of applications. Like you can use regression and other things, not just clustering, and then apply it, and it gives very good results and many applications. So I encourage you to look at the literature to see more applications and see if it can fit some of the things that you care about. I'll stop here. Thank you very much.
Let's thank Robbie. And at this time, we are taking any questions on the chat. Okay, so there's a question from Sandeep. Do you want me to read it? Yeah.
Just a second, let me open it, move it away.
Sure.
Okay, yeah. From Sandeep. Can these corsets help with other type of graph clustering, such as spectral clustering, for example? Only do spectral clustering on the corset vertices. Okay, that's an excellent question. I have not seen this version of corsets. I find it very interesting because, I mean, for me, it's exciting that you can get something with accuracy 1 plus epsilon. I've worked a lot on, approximation algorithms, factor 2, factor log n. You always get something which is very nice theoretically, but it's not clear if it works well in practice. 1 plus epsilon is very promising, and you can often compute it in linear time. So I don't know specifically about this, but it's sort of like turns out to be effective in many places. So I'll be optimistic. That's it. Okay, should I move to the next question?
Right, sure, yeah.
Okay, let me know if you run out of time.
Sure.
What is the lower bound on epsilon for constructing Euclidean corsets? Very good question. So I think there were very little work on this over the years about in the tree-width paper, because I presented here 2 papers. In the tree-width paper, at least in one of its versions on arXiv, there's a lower bound of 1 over root epsilon. I think k divided by root epsilon. Okay, so it's not only dependent only on epsilon. And I think that's the best known at the moment for Euclidean corsets. There's a gap between square root epsilon and square, right? So it's even bigger. Question from Tachafon. Can we construct these corsets deterministically? Okay, that's another very good question. I don't know for sure. I discussed it recently with Xiaofeng, one of the co-authors, Xiaofeng Jian, and we looked at it. So I don't know for sure, maybe other people know better, but I think some of the early results, the exponential in dimension, were deterministic, I think. Okay, so they definitely work. The ones that you see here, the latest ones, are based on sampling. For these samplings, I think no de-randomization is known, or for these tools that we use. There may be some de-randomizations, but I don't think they apply here. So potentially it can be done, right? Like, so there are some papers that talk about how to do sampler, what's called a sampler, epsilon sampler. Maybe there are de-randomizations for those problems that are useful here. I don't know of any at the moment. From Rajesh Jairam.
I think he's sending another message afterwards. So I think maybe it's a good time.
Okay, that's a low one. Okay, yeah.
Yeah, so let's thank Robbie again.
So thank you very much, and thanks to the organizers as well.